let's take a look at even, odd, or neither. All right, graphically, here is what an even function is going to look like. Okay, it could look like a parabola. The parabola could be flat, roundy. It could also be a graph that looks like this. Up, down. Okay. Both of these have something in common, and what you have to remember is that even functions, okay, are symmetric to the y-axis. So if you were to take your paper and fold your paper, the graph would match exactly. Okay, same thing here. So even functions are symmetric to the y-axis. All right, let's take a look at some odd functions. My favorite odd would be x to the third. Something like this. Okay, x to the third, of course, is an odd number. It could be even fancier. It can come up and then down and then back up again. Okay, so that's another cubic. That's also odd. And how do you do odd? Whenever I look at the word odd, that kind of reminds me of the origin. They're symmetric to the origin. How did you do an origin test? You put your pencil on the origin, you spin your paper upside down 180 degrees, and the graph looks the same. If you turn it upside down and it's exactly the same after you spin it upside down, then it is odd. Okay, so odd, symmetrical to the origin, you spin 180 degrees, and it has to look exactly the same. Okay, so those are even, those are odd. Now, if you don't have a picture to look at, how do you figure out algebraically if something is even or odd? So what you do is you calculate f of negative x. So when you take the function and you put in a negative x, and then you do work, and then you do work, if you get f of x, then it is even. So if you put a negative in and you get the original back, then it's even. When negative x is plugged in, comma, then we get the original. You get the original, exactly equal to the original f of x. Now, what do you do if it's odd? Now, the test is the same. So you're going to calculate f of negative x, and you're going to calculate, but you don't get f of x. What you get is negative f of x. So your f of x function is the opposite. So in words, when negative x is plugged in, okay, comma, we get the opposite. We get the opposite. I should say then we get the original. Okay, let's practice these calculations a little bit so we can figure out what even and odd is. So the test is the same. When it says algebraically determine, you need to show lots and lots of algebra. Okay, so here's f of x. I'm going to calculate f of negative x. We're going to put a negative into the function. So I'm going to make sure that I use some parentheses here. So we're going to do negative x raised to the fourth power minus 2. There's your x, there's your input. So let's use parentheses because our input is a negative x has to get squared plus 5. So first you show me a line of work of the negative x going into the function. Now we're going to continue to do some work. A negative raised to an even power becomes a positive. This becomes positive, so we still have minus 2. Now don't forget, x squared is x squared. Negative times negative becomes positive. All right, now let's examine what we got. Is this the same as the original? Exactly the same? Exactly. Yes. Since f of negative x is the same as the original, then we say, therefore, even. Everyone always asks me, what does this symbol mean? That means therefore. Therefore, I'm going to say even. I put that in the notes, therefore. Okay, just a nice way of mathematically saying I conclude even. Let's try another one. Let's calculate f of negative x again. So it's the same test, we just examine the results. So your negative x has to get cubed. Don't forget to use parentheses. And then we're going to have plus a negative x. Then we have minus 1. Okay, so now we're going to simplify our results. A negative to the third power is negative x cubed. This is minus x minus 1. Okay, here's my result. Is that the same? Is that the original? Oh, absolutely not. Is that the opposite? X cubed is negative. That's opposite. Positive x, negative x. That's opposite. Oh, wait a minute. That's not opposite. Right there, not opposite. So it's not even. It's not odd. You're going to say, therefore, neither. Therefore, neither. Okay? So here's a little note. All terms must be opposite, not just some of them. All terms must be opposite. All right, let's take a look at another one. This one's interesting because it's a fraction. So I'm going to calculate f of negative x. That's 5 times the negative x. In the denominator, make sure you use parentheses. If you don't, it's technically not correct because the negative and the x have to get squared. Okay, so f of negative x, what do we get here? I got negative 5x in the numerator. Negative times negative is positive x squared minus 7. Okay, now this is what I want you guys to do with fractions. All right, whenever you have a negative in the numerator, okay, or even the denominator, I want you to write it out in front. So we're going to take that negative, pull it out in front, and then I want you to write the fraction in parentheses like this. Is that true? Would a negative get distributed to the top, the bottom, or both? Well, it can't go to both because then it would be a positive. So the negative would only go to the numerator, which is what that is. Okay, so this is legal. Now let's examine this. This fraction is exactly the same as the original fraction, except it's the opposite of the fraction. So therefore, this one is odd. Okay, so there's a little trick there when you have a fraction. I want you to pull a negative either out in front from the numerator or possibly from the denominator, wherever he has a negative. And this fraction is odd. So let's just write a little note here about fractions. The opposite of 1/2. What's the opposite of 1/2? The opposite is negative 1/2. Okay, or we could have 1 over a negative 2. There's a negative. Or probably it's best to put the negative out in front and then say 1/2. The opposite of positive 1/2 is negative 1/2. But that negative sign might be down there or it might be up there. So the best thing to do is to take that negative, pull it out in front, and then you're going to be very clear that it's the opposite of the fraction. Okay, that's how you algebraically determine even or odd. You could also graphically determine, but sometimes the graph is just a smidgen up or down. If this hump was a little higher than that one, it would not be even. So algebraically doing things is the best because you don't get it wrong. Okay, increasing, decreasing, and constant. I take a look at this function. Okay, a function is going to be increasing between x1 and x2. Okay, if the graph goes up. And what that means is the y values are going up. So right here, you start on the left. So from left to right, I'm going to put that note up at the top. Okay, you always go from left to right, just like you're reading a book, left to right. So you start here on the left. This function goes up, then it goes down, then it levels off, then it goes down. So where is it increasing? Okay, right here. Here it's increasing. So highlight the increasing. There's just one increasing section, and I'm going to state it using interval notation. So it starts here at parentheses negative infinity and goes and goes and goes until Okay, do we use x values or y values? It's like domain. Yeah, we're going to use an x value. Now what I'm going to do is put a bracket on it because that is a closed point. That's not a hole. I don't want to make a hole. I want to make sure I have a nice closed point there. Okay, let's take a look at some decreasing. It's decreasing if the graph and if all the y values go down. The graph goes down. So here is a decreasing section, and here is a decreasing section. So we got two decreasing sections. So I'm going to say from 5 to 8, from 5, 8, and those are close points. So I'm going to use brackets on them. I don't want to make a hole there. And another piece. So let's say union from 13 brackets all the way up to 16. So it's like we're stating the domain, but I only want the domain for the parts that are going down. So it's like domain. And finally, we have a constant function. Okay, if y values are the same, okay, or you could say the graph is horizontal. If the graph is horizontal, then it's constantly. So here's a section of constant. And again, let's state the x value. It's like domain from 8 to 13, brackets, 8 to 13. Okay, so let's just be clear here with some notes. To write the intervals of increasing, decreasing, constant, let's state the x values. Okay, let's state x values, like domain. Okay, it's like domain, except you have to state the domain for the part that's either going up, down, or constant. We are going to use our calculators a little bit to state intervals of increasing, decreasing, constant. So let's get out those calculators and type our equation into y1. So we've got x to the 4th minus 7x squared plus 6x. So let's get that all typed in. And I'm going to try to see if the standard window works. So let's just give Zoom Standard a try. It looks like we might have to go down on the y-axis. So let's change our y-axis minimum to -30. I am going to change my scale to 5, just so I don't see so many tick marks. Otherwise, I'd see 30 marks there. Maybe just to clean it up a little bit, I'm going to change the X window to 5s as well. Just get in a little closer. Okay, I think I see what's going on here. This graph is going down, up, down, up. Remember, left to right, like you're reading a book. You're driving the car this way. Downhill, uphill, downhill, uphill. Okay, so I'm going to draw a quick sketch of what we see here. The graph goes down, up, down, up. And we have to state intervals of increasing, decreasing, constant. We don't usually have a whole lot of constants when you're using your calculator. Okay, so this graph has a couple of things happening. Does it have increasing? Yes. And does it have decreasing? Yes. So the graph goes down, down, down to that point, up, up, up to that point, down, down, down to that point. So I'm going to need to find those local max and minimums. So let's go ahead and refresh everyone's memory on how to find a local minimum. You go second, calculate. The minimum value, number 3. Okay, now let me tell you a couple things. You could go, click, 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 click. Did you know you could also type a number? Since this is -5, I'm going to guess -4. And I'm going to guess -1. And then to guess, you could either type a number or just kind of click a couple places in, but you can type numbers for your boundaries instead of click, 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 clicking. So that minimum to 2 decimal places is -2.06, comma, -24.06. What I would really like for you to do is pause this video Find the local max, the local min. Come back when you have your answers. Okay, I hope that you actually did this and got those values. Now it's time to state the increasing, decreasing intervals. So let's just do this as it comes. I'm looking at this graph and it's going down, 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 down. I'm going to do decreasing in orange. Then it goes up, 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 up. Here's another down, down, down. Then it goes up, up, up. So I have to state this one and this one for decreasing. Okay, here we go. Remember, we're using x values from negative infinity with parentheses all the way up to, which value do we use? It's the x value, negative 2.06. I'm going to put a bracket because that's not a hole. I don't want to make a hole. Is there any more decreasing? Yes, one more section there. So union from here to here. From x value to x value. Brackets, 0.46 all the way up to 1.60 brackets. I always use brackets unless it's an infinity because I don't want to make a hole. Okay, were there any increasings? Yep, there was a couple of increasings. From here to here, I'm going to highlight them in green. And then here. So there's two increasing sections starting at x value again, negative 2.06, all the way up to 0.46 brackets. And then here's another union. Here's another piece, brackets 1.60, all the way up to infinity. As long as you remember to use x values, you'll be okay. And put brackets so we don't make any holes. This is a continuous piece. I want to make sure I have all those points. If you put parentheses, parentheses, then we'd be losing those. Okay. Here is one more example we have. This again looks something like a calculator would give you a function that's curvy. Nothing's flatlining here. So at what values does he have a local maximum? Okay. Local maximum. So the local maximum at what x value? What x value? He's got a local maximum at x equals 1. What is the local maximum? This is plural here, local maxima. The local maximum point is 1, 2. So when it says what value, it means x values. When it says what are the local maxima, remember that's a point. That's a point. Okay, does he have any local mins? Yes, he does. He does. So at what values is there a local minimum point? Well, here's a local minimum at x equals negative 1. And here's one. This is the point 3, 0. So at x value, 3. What are the local minima? Local minima mean the local minimum points. So we've got one at negative 1, 1, and one at 3, 0. So when it says what are they, make sure you say points. Points. When it says at what value, that means at what x value. And list the increasing, decreasing, constant intervals. Okay, this graph only has increasing and some decreasing. Increasing, decreasing. All right, let's highlight them. First, the graph, let's see, starting on the left. First, the graph goes down, 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 down. Then the graph goes up, 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 up. Then it goes down, 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 down. And then it goes up, 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 up. Okay, so where is the graph increasing? From here to here. So let's use some x values from brackets. Negative 1 up to 1. Union, here's another piece of increasing starting at brackets 3 all the way to where? Infinity. And what do we always put on infinity signs? Parentheses. Okay, the last thing we have to do is the decreasing sections. We've got 1 and then 2, and we'll do them in order. So start at the left and always state them from small to big. This piece comes first. Negative infinity up to negative 1. Union, brackets 1 to 3. And if you look at this, you should have all those intervals. Every single piece of the graph should be here somewhere. Negative infinity, negative 1. -1 to +1, +1 to 3, 3 to infinity. We've covered the entire graph. All the pieces should be represented there. Okay? So can you graphically determine even, odd, or neither? Graphically means you look at the graph. Good. Algebraically means you do f of -x. And there's 3 things you're looking for. Even is the original. Odd is the opposite. And if it's half original, half opposite, then you say it's neither. And can you use x values to state increasing, decreasing constants? So it's kind of like domain, but just where they want to know up, down. Great job, everyone.